Good afternoon to everyone. I would like to introduce myself. My name is Saud Alsaghir from King Fahd University of Petroleum and Minerals. And my presentation title is Casing Wear Volume and Factor Under Rotation and Sliding Motion. Mechanical wear occurs between the tool joint and the casing in oil and gas wells. And therefore, the wear factor should be measured. And it is very important parameter to assess the well integrity. Therefore, the objective of this study to investigate the effect of the rotation and sliding motion on the casing wear volume and factor for three different types of steels, and study the effect of the side load on the wear factor. In Merah work, only in 2060, conducted an experimental study and found that as we increase the rotational speed and the side load, the wear factor will increase. And B110 steel was the least sensitive to wear. And Osman, 2022, provided an experimental study and found as we decrease the rotational speed and we increase the side load, the wear factor will increase. And in our experiment, we are going to study the effect of both rotational and combined rotational and sliding motion. An experimental procedure to simulate the drilling operation in oil and gas wells. We have modified a lathe machine where we have removed the cross feed and the transfer feed hand wheels, and we used servo motors coupled with a gearbox, and also we have used a program closed loop system to maintain a constant side loads. And we have designed a casing holder to fit any type of casing size. In addition to that, a circulation pump compact with the lathe machine was used to create an lubricant environment. And we have mount a strong magnet at the bottom of the fluid reservoir to absorb any flakes or contamination from the metal. For the measurement, this is a real picture from our experimental setup. We have used in situ displacement indicator to measure the wear depth. And this in situ displacement measure was calibrated before with previous experiment with 2D and 3D optical profilometers. And the error percent was less than 10%. To measure the side load, we have used dynamometer. And we have inserted the thermocouple on the casing surface to measure the temperature during the test. Once we have received the sample, which are real field samples, we have determined the composition of the B110 L80 SM2535 composition using optical emission spectrometry, and the hardness of the three casings and the drill pipe joint measured using universal hardness testing machine. The experimental parameters are rotational speed of 150 RPM, sliding speed of 2.5 millimeter, or penetration rate, side load of 1,000 Newton and 1,400 Newton, and the environment was oil-based lubricant. In result, this is the elemental composition of the three casing steels. We can observe that SM2535 has the least carbon composition, while B110 has the most. And we can also observe that SM2535 has high composition of chromium, nickel, and molybdenum. And the material hardness are shown in the right table. As we can observe that the drill pipe has the highest hardness, and this is the reason why the wear occurs on the surface of the casing. If the inner radius of the casing and the outer radius of the casing is known, we can measure the wear volume using the equation number 1, where we can measure the crescent shape volume. In addition to that, equation 2 shows how we measure the wear factor, which is a common formula used to measure the wear casing. Which is the wear volume removed divided over the sliding distance multiplied by the side loads. And this is the output result. The left figure shows the wear volume of the 3 casing steels B110, L80, SM2535 under only rotational speed of 150 RPM and 2 varying load, 1000 Newton and 1400 Newton. We can observe that for all the three types of steel, as we increase the side load, the wear volume will increase also. The right figure shows the wear volume for the 3 casing steels under combined motion, sliding, and rotational speed, and the sliding was 2.5 millimeter per second. Also, in this case, we can observe that as we increase the side loads, the wear volume also will increase. In the wear factor measurement, the left figure shows the wear factor for the 3 casing steel under rotational speed motion only and 2 varying load. We can observe that B110 and L80 has less wear factor than SM25. And we can also observe that as we increase the side load, the wear factor will also increase. But what is interesting, after we add the rotational, after we apply the sliding motion, I can say almost the wear factor for the 3 casing steels are comparable. And to understand the sliding speed affecting the wear factor, these 3 figures are shown for B110, L80, SM2535. The blue column represents the rotational motion only, while the orange column represents both the combined of the rotational and sliding motion. We can observe that B110 and L80 behave similarly when we apply the sliding motion of 2.5 millimeter per second, the wear factor increased by a factor of almost 200, while SM2535 has slight effect, where the wear factor increased by almost a 4. These are some of the experimental samples, B110, L80, SM2535. It showed the crescent shape and the worn surface. And the worn surface was analyzed with my colleague previously. In conclusion, it was found that as we increase the side load for all the 3 types of casing steels, the wear volume will increase also. And it was found also that B110 and L80, the combined motion has most effect on them. And in general, the combined motion of sliding and rotation result in much higher wear factor for all of the 3 types of casing. And this is possible explanation because now we have a friction on tangential to the casing and axial to the casing. In addition to that, we have a thin lubricant film. It might be affected by the sliding motion, and there was a turbulence. And this is the reason why the wear factor increases. Thank you for listening, and now back to the same question.